Good. So welcome again. Today, we will mostly see how you can produce high energy particles from different type of sources. And this will lead me straight to then starting with some exotic processes that can inject energy or new particles in the medium. So, but first of all, we have to at least have an idea, a rough idea, where standard cosmic rays do come from. So I will start with some more description of astrophysical sources and cosmic ray accelerators. So what we have seen in the past lectures has been basically how, if you have these cosmic ray particles injected into the interstellar medium, what are the processes that leads to the production of photons, neutrinos, and other cosmic rays, right? But I never told you how, indeed, high energy sources can accelerate and produce particles, and most notably, often I told you that the particle energy distribution was proportional to a power law without explaining you why we believe so. And this is what I'll do in the first part of today's lecture. So in order to get back a bit to the energetics and to understand where these sources are, because remember, so we have high energy astrophysical sources in the galaxy, and we have extragalactic sources. So depending on the energy, we want to understand what is the origin of cosmic rays at different energy. So what we have to explain is this all-particle cosmic ray particle spectrum, which spans many order of magnitude in flux and in energy. So of course, although the spectral shape of this emission is basically featureless, what we want to understand is what is the origin of this cosmic ray. So first of all, we have to check what is the energetics of galactic accelerators. So what is the maximal energy at which galactic sources can accelerate cosmic rays? We'll see that in the standard paradigm, this is at about 10 to the 15, 10 to the 17 electron volt. And then it means that in order to explain observations that we have made of ultra-high energy cosmic rays, but also ultra-high energy photons, the parent population of proton that originates this kind of high energy emission should come from extragalactic sources. So the current status is that we don't really know where this transition from galactic accelerator to extragalactic accelerators occur, and this really depends on the details of the models, but it's clear that for galactic accelerator, this is very difficult to push higher than 10 to the 17 electron volts. So we will see now in more details why it is so. So to do that, I'm gonna start from how we can accelerate particles in different objects. So when you want to accelerate cosmic rays, you need some basic requirements. And in particular, you need to extract energy from the cosmic ray source in order to be able to inject energy in the particles for particle acceleration. So depending on the object, there are several mechanisms to accelerate particles. We'll see in a bit of detail only the acceleration in strong shocks that are occurring in supernova remnants, but there are other source of energy that can be extracted by the accelerator, like the rotational energy in a pulsar or the energy from accretion onto accretion disk in IGN. And these allow for energy transfer from the accelerator to the particles, and then you need for the particles to be confined for a long time in the accelerator to acquire enough energy to be able to escape into the interstellar medium. So, as I mentioned, we'll see just one type of particle acceleration, which is one of the standard paradigm that is taking place in strong shocks. It goes under the name of diffusive shock acceleration. We see just the basics, and not all the details of the theory that has been developed in the past 10 to 20 years. But I would like you to be aware of this mechanism for particle acceleration and why it is so important. So there are two main mechanisms for stochastic acceleration, and the first one goes under the name of second order Fermi acceleration, and it was put forward by Fermi himself in 1949, trying to understand what is the dynamics of particles that could be reflected by what he called magnetic mirrors or magnetic clouds. So the idea is the following. So you can approximate any irregularity in the, for example, magnetic field of the galaxy as like a planar disk. So this is your magnetic mirror. And what it occurs, so particles are in the interstellar medium, will encounter these irregularities in the magnetic field, for example, and will get deflected by the presence of these magnetic mirrors. So what it was really the key point of Fermi work is that he demonstrated that particles that cross these magnetic mirrors do gain energy. Okay? So particles can cross the mirror in this direction, so this is an head-on collision, or they can cross the mirror in the other direction, this is a tail-on collision, and then they get reflected back, so they will cross and cross again, and at each crossing, the main point is that you have a gain in energy. So let's suppose that this magnetic mirror is moving with a given velocity in the interstellar medium. So you can define a beta factor. So one can show that the gain in energy per crossing average over all possible directions of the incoming particles is proportional, or is equal to 4/3 beta square with correction of higher orders. So I won't go into the derivation, but the main point is that you have the dependence of the average gained energy, which depends on the beta factor to the square, and this gave the name of second order Fermi acceleration mechanism. However, if you look at typical values of beta for, let's say, clouds in the interstellar medium, these are order of 10 to the minus 5, 10 to the minus 4. So the acceleration cannot be very efficient if you just think about cosmic ray accelerated by irregularities in the magnetic field. So you need another mechanism or another environment where something similar takes place. And what people have investigated then is what happens at the boundaries of shocks. So shocks, you can think of a shock like a discontinuity in the macroscopic observables. So this is the shock front. And it might be I mean, it's something that, for example, it occurs, it becomes generated when a supernova explodes, and then it ejects the material around the supernova, creating a shock front in the interstellar medium. So what defines a shock front is basically you have a discontinuity of all the macroscopic quantities like density, velocities, and temperature. And yet, at the shock front, there should be conservation of these quantities and validity of conservation laws. So typically, you will see that we can define what is called the upstream, which is basically the interstellar medium behind the shock, and the downstream, which, for example, can be the supernova remnants itself. If the shock is moving, again, with a given velocity, in the rest frame of the shock, the upstream is moving towards the shock with the velocity u1, and the downstream is moving away with velocity u2. So now, depending on the conditions of the velocity of the shock, what we can define is the Mach number, which is the velocity of the shock divided by the speed of sound in the medium. And the Mach number can, if it's much larger than 1, so the shock is traveling at a much faster speed than the speed of sound in the medium, then this defines strong shocks. So we'll work on the approximation of strong shocks in order to derive the main particle emission spectrum, but the theory of diffusive shock acceleration can be generalized to any other Mach number. Okay. When the shock front is moving, as a matter of fact, there is a compression of the interstellar medium in the upstream region. So there is a variation of the adiabatic index of the medium, and this compression factor, take this expression, where gamma is the adiabatic index of the medium. And in particular, if you have a monatomic ideal gas, this gamma is 5/3. Okay. So people have studied the dynamics of the shock and the kinematics, and they have found actually that the gain that a particle has at each crossing in the shock is proportional, in this case, to the beta factor of the shock with higher corrections. So the difference between mostly the two is given by the different distribution in angles. And you see here that this depends on the velocity to the first power. So this is what goes under the name of first order Fermi acceleration mechanism. Okay. So this is the fractional average energy that a particle gain in each crossing of the shock. So a crossing will be to go from upstream to downstream and then back to upstream. So this is one crossing, and this is the average fractional energy that the particle gain. So now let's consider that you have a total time, t, in which the particles can then do multiple crossings, and if it does take time tau to do one crossing, then you have the total number of crossing to be T divided by, capital T divided by tau. But of course, there will be a finite probability for the particle to escape completely by this continuous crossing. So we will call this escape probability, so P escape, which also imply that there is a probability 1 minus this P escape for the particle to continue crossing. So with this probability, a particle of energy En will gain energy in one crossing and will have the energy at the subsequent crossing given by 1 plus C En, okay? So what we want to know is what is, given an initial energy E0 of the particle after a time capital T, what is the energy that this particle has gained because of multiple crossings. So the energy will be 1 plus C to the N, and this will have a probability with probability equal 1 minus P escape to the N. So if we are then interested in the cumulative particle spectrum, so what is the spectrum of all the particles that have energy larger than this energy, this is proportional to the sum over all possible crossings of the probability escape. And this is the geometrical series that we can expand. So this is also equal to the N divided by P escape. And now, because of the relation between the energies, so now we want to know what is the relation between, so what was that here? Sorry, the relation between the energies. We can also relate this index N to the energy that we are interested in. So we can show that this is also equal to 1 minus P escape divided by P escape, where this exponent here is related to the ratio of the logarithm of the energy at which we want to evaluate the cumulative spectrum divided by the initial energy divided by the logarithm of 1 plus the energy gain, okay? So then we can further expand the logarithms and get an expression of the cumulative particle spectrum. So now, just with the properties, okay, of the logarithms, we can show is equal to 1 over P escape E divided by E0 to the minus alpha, where alpha is the logarithm of this quantity to the minus 1 divided by the logarithm of the incremental gain. And if in the limit in which P escape and psi are small, then we can approximate this by the probability of escaping divided by the average gain per crossing. So first of all, you can recognize that there is a power law that is popping up. This is the cumulative spectrum. And the exponent of the power law is related to the microphysics of the crossing in the shock. So now what we want to know is to have a prediction for the numerical value of this index here, because we can work out the details of the probability of escape and psi. So psi we know already, this is proportional to the beta factor of the, yes. The beta or the psi? Beta, okay, beta is simply the velocity of the shock divided by the, yeah, is the beta factor of the shock, yes. Okay. So we know psi. Let's work out what is the expression for the probability, the escape probability. Okay. So just like a reminder of the thing, of some basic definition. So we have seen in the very first lecture the definition of particle flux. This is also related to the intensity of the radiation, and in particular, if you consider the flux, so this is the definition of the flux as a function of the intensity, where delta omega is the solid angle. If you want to compute the particle flux that is coming from just one hemisphere in a planar shock, so that comes only, let's say, from the upstream direction, then you can show that this is related to the, let's call it phi. So you want only the flux that's coming from one direction, which is the upstream direction. Okay. So now if you consider and did like a shock and you want to compute the particle of flux that is coming towards the right from the upstream direction, you can relate the flux to the particle distribution. So then this will be the flux as a function of energy. And the intensity in general is related, just to remind you here, the intensity is related to the flux number density through this relation here. So then you have the flux, the rate of particles entering the shock from the right direction. Okay, is related to the number density of particles. Okay. Okay. Now let's consider the downstream region. So if you are far away from the shock in the downstream region, then there is the flux of particles that can escape the shock far away from the shock, that are advected away, will be proportional to the velocity of the downstream times the flux particle, the particle flux. Okay? So then you can define what is the probability of escaping as the ratio between the flux of particles that enter the shock divided by the flux of particles that can escape from the shock divided by the total number of particles that enter the shock. So it does not depend on the particle flux, but it only depends on the velocity in the downstream region. Now let's go back to the definition of our alpha there, because this is what we want. So it's the ratio between the probability of escape and the average gain. And this was third, the velocity of the shock divided by c, but in the shock rest frame, this is nothing else than the difference, the relative velocity between the upstream and the downstream velocity. So we can replace it here. Okay. So this is equal to 3 divided by r to the minus 1, where r by definition is the ratio between the velocity, and this is also the compression factor. So in strong shocks, you have that these are, so let's say, let me write here, so velocity is u1 minus u2, and r is also equal to u1 divided by u2. And r from strong shocks is equal to 4. So in strong shocks, then this alpha is equal to 1. Now let's go back to the cumulative particle flux. Okay? So this is the cumulative flux in energy, which means that by definition is the integral over energy of the differential particle flux. Okay? So then if the exponent of the cumulative flux is alpha minus alpha, then the exponent of the differential particle flux will get a plus 1, a minus 1, so it will be proportional to e to the minus 2, given the fact that alpha is equal to 1. And this is the demonstration under ideal conditions of the shock that the particle energy distribution of particles accelerated in a strong shock has a universal index, which is minus 2. And this is where this infamous minus 2 that often we assume for cosmic ray sources, this is where it does come from. Okay. So there are several characteristics of this. So as you see, the index does not depend on the characteristic of the velocities, of the densities of the shocks. You know, it only depends on this compression factor, and so it's truly universal in strong shocks. And just to be extra careful, this is the spectrum at the source. It does not mean that is the spectrum of particles once they are escaping and injected into the interstellar medium. So there might be indeed in the supernova remnant right behind the upstream, you have the interstellar medium, so these particles can then interact with the gas of the interstellar medium directly at the boundary shock and modify this spectrum, okay? So there might be complications that are ongoing that depends on the specific environment of the cosmic ray accelerator. but the acceleration spectrum has this shape. Good. Now, as I mentioned before, you need some time, right, for to have enough crossing to make an efficient particle acceleration. So a necessary condition for the acceleration is that particles are confined long enough in the accelerator in order then to be able to gain energy. So if you want, there is like a necessary condition for the acceleration, which is the confinement. And that requires, so typically the shocks are all these environments for particle acceleration needs to be strongly magnetized. So a particle can be confined in the accelerator if the Larmor radius is smaller than the size of the accelerator. Now, if you remember the definition of Larmor radius and rigidity, so the Larmor radius is connected to the rigidity of the particle and the magnetic field of the accelerator. Okay. And so the confinement condition, which is this one, set a relation between rigidity, magnetic field, and size of the accelerator. Now, so there is a relation that must be respected in order for the confinement to occur that relates the size of the accelerator and the magnetic field. In particular, the rigidity is the momentum divided by the charge. So for relativistic particles, this is equal to the energy. So this condition of confinement defines a relation between the energy, the magnetic field, and the radius. And you can define, for any accelerator, you can define a maximal energy up to which you can accelerate cosmic ray that more in general will depend on how efficient the shock or the accelerator is in accelerating particles. So this is the acceleration efficiency. Depends generally on the beta factor of the shock, so how fast the shock does move. Depends on the charge and the charge that you want to accelerate, so the charged particle that you want to accelerate, and the magnetic field of the accelerator. The size of the shock, better the size of the accelerator, and eventually if there is some bulk motion of the shock with a gamma factor. Okay, so there is then a plot that you can have. Yes, this I will tell you later. This is the Hillas plot that for each maximal energy that you are considering defines along this diagonal line here is the minimal product between magnetic field and accelerator size that allows you to accelerate particles at that energy. So it means that you can accelerate particles with energy larger than 10 to the 21. This plot is for protons. If the product of B times R is larger, so it falls here. So if you have models for the different particle accelerators, you can put them on this plot, and this is what is done here. So you have several classes of possible particle accelerators. So you have the supernova remnants, you have pulsars, you have extragalactic nuclei, you have GRBs and other and other objects. And what you can see, this is like a qualitative way to show you that, for example, if you want to accelerate protons at energies larger than 10 to the 20 electron volts, then supernova remnant cannot do the job. So it means that by the fact that you observe ultra-high energy cosmic rays, it means that there should be other source classes that should do this job. And this allows you to, going back to the particle acceleration, spectrum, measured particle spectrum, to understand where should be this transition between galactic and extragalactic accelerators. Questions so far? If not, let's have a look qualitatively at a few particle accelerators. So as I mentioned already, supernova remnant, where the mechanism for particle acceleration are diffusive shock acceleration. So what we observe is that we see supernova remnants. I mentioned that already yesterday, and we know that proton acceleration should be ongoing in these objects. So the typical shock velocities are of the order of 1,000 kilometers per second. The magnetic fields are of the order of the microgauss, and this, in this very simple model, you can then get that the supernova remnant can accelerate at most up to 10 to the 17 electron volt. So what we observe, what we know from supernova remnant, we see them from radio up to gamma rays. We have detected this pion bump, as I showed you in the past lectures, which is really the smoking gun signature of proton acceleration. And we see supernova remnants of different ages and different types emitting up to TeV energies, but we do not see them to accelerate particles up to PeV against the expectation that can accelerate up to the 10 to the 17 electron volts. So it's still not clear if this very simple expectation is correct, and we don't see them because of some systematic observational reason, or if really, in the end, supernova remnant cannot be what we call pevatrons, so that can accelerate particles up to 10 to the 12 electron volts. The other, one of the other very important particle accelerators are pulsars. So pulsars are rapidly spinning neutron stars that emerge at the final stages of the end of stars. So when, for example, you have a core collapse supernova and you have the formation of pulsars. And they have very strong magnetic fields and very small confinement size. So they are really extreme objects for which we measure radiation in photons from radio. So they are emitted primarily in the radio band, but also at higher energies at GeV, and most probably those are the sources that are underlying the detection of pevatrons at the PeV scale. And indeed, Lazo has observed probably now even more than 10 pevatrons, and 9 of them have a pulsar associated in the nearby region. So it seems that they are very good candidate for emission of particles at the ultra high energies.
When you say supernova remnants, you mean very young neutron stars?
So when I say supernova remnants, is really the shock, is the shock front that develops when the supernova explodes. So it's the ejected material. So that is the boundary. It's the leftover of the supernova. And there's this shock at the boundary where you can have this crossing and acceleration. Here, for pulsars, the mechanism is different indeed. So I won't go through it. I will explain some basics of the pulsars. But in that case, you have really that is the magnetic energy of the pulsar that can extract particles and accelerate them in the strong in the magnetosphere of the objects, and then they can escape.
So essentially, this context supernova remnant is the compact object at the center plus the ejected envelope, right?
So there is a bit of zoology now that, if I remember correctly, when so you have the supernova that does the core collapse. Then you have the formation of the shock, the supernova remnant, but sometimes, so the pulsars, depending on the age of the supernova, it might be either still at the center, or it can have transitioned outside the remnant. So when we talk about remnants, I can show you here. You don't see the neutron star at the center. So there are some supernova remnants that do have the neutron stars at the center. There are some of them where the pulsars has left the supernova and is isolated, because there is like a kick velocity that the pulsar receive during core collapse. So the pulsar and the remnant might be not one inside the other. Okay. So eventually the supernova remnant is this part here, is the remnant front. You can have the compact objects inside it, and this will be a neutron star. It will do its own particle acceleration. And you can study what is the emission that comes from the accelerated charged cosmic rays by the pulsars in the environment of the remnant. But this will be a different mechanism than particle acceleration at the shock front. Okay, let's see a bit more, some basics about pulsars. So the idea here is that you have a star that at the end of its life does collapse, and the remnant of this the star after collapse is a neutron star. So, and the radii of neutron stars are, compared to the radius of the sun, are of the order of 10 to the minus 5, so much smaller. And the standard paradigm is that neutron stars are born with strong magnetic fields and are in rapid rotation. And the fact that they spin rapidly is due to the conservation of angular momentum during collapse. So here I is the moment of inertia of the star, which is proportional to the mass of the star times the square of the radius. So now let's just take the sun as an example. So the sun has a period of rotation of about once per month. So its rotation period is 10 to the 6 seconds. And if you imagine the sun to be contracted down the radii of a neutron star, which is about 10 kilometers, then you'll end up having periods of the neutron star of milliseconds. So because of a conservation of angular momentum, they should be rapidly spinning. Now let's consider the magnetic flux of an ideal conductor, which is the product of the magnetic field, the modulus of the magnetic field times the area. Then if you consider the neutron star as a perfect sphere of radius r, then again there is a relation between the magnetic field and the radius of the star that has to be conserved during collapse. So if you start with a star of about 10 to the 4 Gauss to start with, then you end up, because of conservation of magnetic flux, with a neutron star that has 10 to the 12 or higher magnetic fields. So this is extremely high magnetic field with respect to normal stars and are objects in rapid rotation. So the magnetic field structure of the initial star is conserved during collapse, and typical stars have dipolar magnetic fields. So the neutron star will be rapidly spinning with a strong dipolar magnetic field, and we can approximate the pulsar with, so then it can be interpreted as a rapidly rotating magnetic dipole. And this is the basis model, the basic dipole. The basic model that allow you to compute what is the energy that is radiated in particles by this kind of object. So for a rotating dipole, you can compute what is the energy of this rotating dipole under the assumption of spherical symmetry. So our pulsar is a perfect sphere, which is not in reality, but for the moment we don't care. So the energy of this rotating dipole is related to the moment of inertia, which is related to the mass and the radius of the star, and the frequency of rotation. So this is the angular frequency, which is related to the period of the rotational period of the objects by this relation here. And what you can compute is also what is the time variation of this energy, so the energy change, which will depend on the derivative of the period and the period derivative. So now in most cases, this rotating dipole is not aligned with the rotation axis. So if this is the rotation axis, the magnetic dipole can form an angle alpha with respect to the rotation axis. And in this case, what you have is that the charge is in rapid rotation, so there is an acceleration, and where is a charged particle that is accelerated, we can again use the Larmor formula for the radiated power. So if you remember, the accelerating moving charge will radiate energy, and this will be proportional to the acceleration to the square power. Okay? So now we have to understand what is the acceleration in this context. So the acceleration is given by the acceleration in the r direction and the sinus of alpha. And we can define the electric dipole moment as the product between the charge and the radius. And so only the transversal component of the electric, let me put it P, of the electric dipole moment, so P is the electric dipole moment. Only the transversal component to the rotation axis will give a contribution to the radiated power. Now, this equation is valid also if instead of electric dipole moment, we consider the magnetic dipole moment. Okay, it has the same functional dependence on the perpendicular component of the magnetic dipole moment to the rotation axis. So this will be the magnetic dipole moment. And the magnetic dipole moment is defined for, again, this perfect sphere by the product between the magnetic field and the radius to the size of the radius of the star to the cube. This is for a uniformly magnetized sphere. So then we can rewrite the radiative power as a function of the perpendicular component of the magnetic dipole moment along with respect to the axis of rotation. And this final expression there is the radiation that is extracted by the pulsar kinetic energy that is transferred to whatever is available to be accelerated. Okay, so this is the way in which this magnetic dipole radiation model can extract energy, and that's the radiated energy available for acceleration. So the fact that you can radiate energy will also mean that your period is decreasing with time, and the rate at which is decreasing is the first derivative of the period related to this omega dot, which has to be defined positive. So we can, so this E dot here is what we call spin down power. Okay, of the pulsar that corresponds to the energy that is lost by the dipole moment per unit time. So there is the rate at which this rotational energy changes because of the fact that this dipole, magnetic dipole in fast spinning is radiating energy. And this is also equal to minus the radiation, okay? So you can work out the fact that while the P dot changes, so the P dot is positive defined, and P will decrease over time because of this slowdown during to this radiation, the product between P and P dot will be constant in time and is related to the magnetic field and the radius of the source and other, and in a moment of inertia. This is B. So what do we measure from pulsars is that we observe the electromagnetic radiation, which is very regularly beamed in radio frequencies. So from observations, we can derive what is the observed period, and we also can measure what is the variation with time of the period, because what radio astronomers do is to follow up a different time interval the pulsar, so to define what is exactly the p dot of the pulsar. So once you have determined experimentally the period and period derivative of the pulsar, then you have access to the fundamental parameters of the pulsars, and in particular to the magnetic field, by making, of course, some assumption on the radius of the pulsar, the mass, and its mass, which enter also here. And pulsars, so as I mentioned before, can then exploit this radiation to accelerate particles or to directly produce prompt emission in the magnetosphere. So typically, the gamma ray luminosity of a pulsar is related to the spin down luminosity through some acceleration efficiency, let's say gamma ray emission efficiency. So the intrinsic luminosity will be just a fraction of the spin down power. And it might also be that, so recently people have investigated also what is, if there is a dependence on the spin down power, which is different from linear, finding that mostly the gamma ray luminosity goes as the square root of the spin down power. Okay. So that is what I wanted to mention about pulsars. We also have extragalactic objects that can strongly accelerate particles, and one of the main mechanisms to accelerate particles is in active galactic nuclei, where you have supermassive black holes that is fueling the emission of plasma and particles along the direction of what we call jets. And in the jets, you can have particle accelerations through and then production of secondary photoemission through the processes that we have seen yesterday. So synchrotron, self-synchrotron, inverse Compton, and anything you can think of in this very highly boosted plasma of particles. So here we are in the fully relativistic regime for all the processes that we have discussed in the past days. There is also, so typically active galactic nuclei are embedded in galaxies where you have the environment around the supermassive black hole, and you have the formation of accretion disks around the supermassive black hole because of the dragging force of the black hole, and the gas get accreted, forming these typically shaped accretion disk, where again there might be some particle acceleration ongoing through mechanisms that I won't have the time to go into the details. But so just to say that the particle emission mechanisms can be of different nature, and you always need to extract energy from the accelerator in order to transfer it to the particles. So depending on the line of sight, so the direction between the jet and the observer line of sight, AGN can be classified in several families. Just want to mention that we because in the literature you may find different names for objects that in the end are more or less the same. So you can have blazars when the jet is aligned along the line of sight. So the jet points directly towards you, or you can have what are called the misaligned AGN if the jet is instead oriented with some inclination angle with respect to the observer. And typically, as I mentioned before, you can produce a truly multi-wavelength spectrum because of the different mechanisms for radiation that occur in and around the jet. So this is what we call the spectral energy distribution, so the intensity flux as a function of frequency for one nearby AGN, Markarian 421, which has been observed with multiple instruments. And this is like the radio, the X-rays, and the high energy gamma rays. So what you see here and what you now can guess is this double bumped structure of the radiation, where the first one is here at high energies, comes from inverse Compton, and the second one comes from synchrotron emission. So there is like a whole chapter of high energy astrophysics, which is trying to understand what are the particle acceleration mechanism and the production of photons in jets, and try to fit and explain this kind of SCD with all the microphysics of the AGNs. So, but how do these objects look like in high energy gamma rays? Because, so we have seen in the past lectures where this bright emission comes from. Again, this is the GV to TV sky. But then you can also see that there are bright hot spots here in red that are distributed more or less isotropically in the sky. So these are high energy gamma ray emitters that from gamma rays only, we wouldn't know what exactly is their nature, but what we can do is to cross-correlate with catalogs of AGNs or other objects in other wavelengths in order to identify what objects are emitting in gamma rays. So most of the point sources, as we call them, that you see here are extragalactic objects. We identify about 5,000 sources in the full gamma ray sky, and 3,000 of them are mostly active galactic nuclei, so extragalactic objects emitting in gamma rays. Okay. But as you see here, there is a part of the sky that for which you still receive photons that are at too high latitudes to be of galactic origin. So what I want you to go into more details now is how sources of cosmic rays and photon will contribute to diffuse gamma ray emission, and this is relevant to interpret and understand the origin of photons from in the MEV sky up to sub-PVE and PV energies. So we have seen you have a contribution from the galaxy, might be different depending on the energies, but it is there. And then there is also a guaranteed contribution to the diffuse emission that comes from objects that are faint with respect to the detection threshold of the instrument, but still do emit gamma rays and will contribute to the diffuse photon sky as unresolved sources. So we have seen that in general we have sources that can directly accelerate cosmic ray and inject them into the interstellar medium, or they can produce prompt photons and neutrinos. So this charged cosmic ray will then produce diffuse emission of gamma rays and neutrinos through inverse Compton and synchrotron radiation, or with interaction, like proton-proton collisions or proton-gamma collisions. But then you can also have direct emission of photons and neutrinos from the source. And in this case, everything depends on the overall flux of the source. So if the source is bright enough to be above the detection threshold of your telescope, this object will be a bright point source in your gamma ray, radio, X-ray sky. But if the object is too faint with respect to the detection threshold of your instrument, then this source will be, as we call it, is unresolved, but it's still emitting whatever radiation we are considering. So it does contribute to the diffuse gamma ray or X-ray sky. Okay. So the energy flux of one source, I will drop the neutrino, but it does apply to gamma and neutrinos as well. So the energy flux of the source is related to the luminosity of the source. So I will drop, I said, okay, by the simple relation of 1/d squared for a galactic object. And if this is extragalactic, you have to take into account the redshift of the source, and it is related also to the spectral index of the emitting source, where here is the luminosity distance, and alpha is the spectral index of the source. Okay. So then for any population of sources, we can compute what is the contribution to the diffuse photon sky by the full population, considering sources that are faint and are not detected as individual objects. Okay, now what we want to look at is the diffuse flux from a given population from source populations. And again, this applies to neutrinos and to photons as well. Okay, in order to do like the inference of this total flux, we have to define what we call a luminosity function, which is a function of the luminosity and the redshift in general, if we are talking about extragalactic objects. And this is the number of sources per co-moving volume. Which well, for some reason in gamma rays, we use the logarithm to express it as a function of the logarithm of the velocity, of the luminosity, sorry. So then with this, starting from this source density, then we can define all relevant quantities that are of interest to understand the contribution of this population to high energy particle fluxes. And in particular, what we are interested in is the collective photon flux as a function of energy of this population, where I told you the luminosity depends on the spectral index, so there will be an integral over the distribution of spectral indices of the population times an integral over the redshift of the population and the luminosity. And the integrand is this luminosity function times the volume element we will always use lambda CDM for reference. Okay. So this, and eventually, that I forgot. It's too long. So there is the final part of the expression. This is the intrinsic photon flux that the F in D. And then there is a like conversion factor because I expressed the luminosity function as a function of the logarithm of the luminosity. It doesn't matter. And then there is the important absorption term because we are considering extragalactic objects. So for any astrophysical population of sources for which you can model the luminosity function, you can infer what is the total contribution to the gamma ray sky. So the way in which you derive the luminosity function might be different, can be fully data-driven, can rely on correlations between different wavelengths, and this really depends on the class of sources that you are considering. And this is an exercise that people have done in order to understand what is the origin of the isotropic radiation that is measured at high latitudes in the Fermi sky. These are the data points, so it's the collective emission of all the photons that are above 10 degrees in latitude and below, so above and below the galactic plane. This is called the diffuse gamma ray background. And you can recognize like a drop in the flux at around 800 GeV, which is due to the EBL absorption, so per production onto the EBL. And here as a featureless power law. So what we want to understand, what people have tried to understand is what is the origin of this diffuse background, but as interpreted as the sum of multiple components by different population of extragalactic objects. And so for each of different populations that you know are gamma ray emitters, here is for the gamma ray sky, you can compute what is the different contribution from the population through the equation that I wrote you there, finding that there are multiple sources that can saturate the IGRB, the diffuse gamma ray background emission. And so an important piece of information has came by the neutrino diffuse emission measurements, because as I mentioned yesterday, when you have photons, you always have, in most of these sources, you have associated neutrinos. And so the origin of this diffuse gamma ray emission is strictly linked to the origin of the neutrino diffuse flux. In the galaxy is simpler if you want, but the same type of argument and reasoning holds. So if you have galactic objects instead, what defines the contribution to the population of sources to the diffuse emission is, again, this luminosity function that this time does not have redshift dependence, but has additional spatial dependence. So most of these sources here we assume to be distributed isotropically in the sky, but for the galaxy, most of the galactic sources are in the galactic disk. So the distribution, the luminosity function in the galaxy can be factorized in one term that depends only on the luminosity distribution of the sources and one term that depends on the spatial distribution of your sources, and the integral over the solid angle, so the volume, and the integral over the density of the luminosity will give you the total number of sources. And in the same way as you do for the extragalactic sky, you can compute what is the total contribution to the diffuse gamma and neutrino flux that comes from galactic sources as the integral over the solid angle and over the line of sight of the density of sources times the integral over luminosities. Okay. So again, for all galactic source populations, what you can do is, provided you have a model which might be informed by multi-wavelength data on the spatial distribution of the sources and on the luminosity function of your sources, you can derive what is the contribution to the total emission. So why I'm spending time on this is that because unresolved sources do play a fundamental role in contributing to the high energy sky. So this is an example of the diffuse emission. So this is the total emission seen by different instruments from a few GeV up to the sub-PeV, where there is a transition from a sky that looks more diffuse, dominated by diffuse processes among cosmic rays, and a sky that is dominated by sources. This is true if we stop in energies at Hess and other Cherenkov telescopes energies, where we clearly see a lot of bright sources in the galactic disk. But if we go even higher, the latest measurement by, for example, LASO, do uncover the presence of a diffuse component in the gamma ray sub-PeV sky, which might due either to cosmic ray processes, so this truly diffuse emission from our galaxy, or, and most likely, by sources that remain unresolved with respect to the threshold of point source detection of the instrument. So every time that you want to interpret the gamma ray sky and also the neutrino sky, when we'll be able to do TV neutrino astronomy in the galactic plane, is that you have your total flux is a sum of, let's say, I'm using photons for reference, but of diffuse emissions that come from cosmic ray processes plus a flux that comes from unresolved sources, okay? So then, and this is mostly in diffuse emission sky, in the diffuse emission sky, that then we may look for additional components of exotic physics. But whenever you want to look for exotic physics in diffuse backgrounds, you have to model and to account for these two unavoidable and guarantee the emission processes. So this has been particularly of interest for the galactic center sky, seen by the left, where we have an excess emission of the detected photons with respect to standard expectation models for these two emissions. So there is an anomaly in the gamma ray sky, which is called the galactic center GV excess, which is an excess of photons in the diffuse emission from the galactic center direction above standard expectations from these two guaranteed components. And so this we'll see tomorrow briefly how people have tried to interpret this excess emission in terms of exotic physics. Okay. This is what I mentioned before, that the very higher energies, we do detect diffuse emission from laser. Okay, now in the remaining 15 minutes that I have, I want to start talking about why do we really care of looking for new physics in this messy place, which is the high energy sky in whatever wavelength you want to work. There are, as you have seen, many contaminations from standard astrophysics. So the main point is that astroparticle observables can have unique features that can allow you to unveil signals and, if not to discover new physics, to discover some new emission mechanisms in high energy astrophysics. And the playground that you have at your disposal is really, really diverse. So the next lecture and the remaining one, I will of course give you a biased view on what you can do in order to look for fundamental physics with astroparticle observables, which is try to cover some of the most important arguments in gamma ray, high energy astrophysics, and neutrino astrophysics, but there are also like avenues to investigate new physics at radio and X-ray wavelengths. Okay, so what I mentioned before is that we can look for exotic physics in two ways. So exotic physics in astroparticle and astrophysics can be due to exotic sources. So as in the case of cosmic ray accelerators, you have extra injection of particles and photons and neutrinos directly into the interstellar medium because of the fundamental BSM process that you can consider. Or exotic physics can also pop up in astroparticle observables through anomalous propagation. Okay, so in particular, I'll try to give you like one example of exotic sources, which is particle dark matter. While for the propagation, I'm mentioning them here, and I hope I'll have the time to describe you them. So what you can have is that there are mechanisms that are altering, for example, the propagation of photons into extragalactic space. So axion-like particles, this you will see next week with Alessandro Mirizzi, can alter the transparency of the universe and have an effect on the absorption and the optical depth of high energy gamma ray sources. You can have neutrino-neutrino, what are called secret interactions that can alter the final distribution of flavors in the ether. And then you can also have We can also test fundamental symmetries with astroparticle observables, like, for example, to test the existence of violations of Lorentz invariance. And other symmetries like CPT, which is related to that. Okay, let's start with a short introduction to particle dark matter. Let's start with dark matter first. So I don't have to explain you that we have overwhelming and multiple evidence of the presence of dark matter at different scales. So what is really crucial for the probe of dark matter is that the evidence for it goes from the scale of galaxies through rotation curves up to the cosmological web background, and is really the cosmological evidence that can allow us to quantify how cold and how much dark matter there is in the universe on average over cosmological scales. And all these observations together, I won't go through them in details, but all those observations together give us the fundamental properties that whatever dark matter candidate has to respect in order to account for this variety of observations at different scales. So, in particular, we know that it should be sufficiently cold to account for structure formation the way we see it. And there are several candidates which might be particle and non-particle candidates that can explain a cold dark matter component. It should be stable, so yes, present on cosmological scales. And if we have a particle dark matter, we can see how we can set a bound on the lifetime of this particle. But again, also non-particle candidate has to be stable over cosmological timescales. And it should be sufficiently massive to behave classically in systems that we observe to be dominated by a gravitational potential that is not due to luminous matter. And with this, from this constraint here, we can derive what is the minimal mass and the maximal allowed mass for different dark matter candidates. It has to be neutral. And we can also measure the cross-section that it should have with standard particles. And in particular, we know that it should be collisionless or not much collisional. So it should have low, we'll see how much, self-interaction cross-sections. Those are very generic properties that dark matter should have that indeed can be accounted for by a huge landscape of particle and non-particle candidates. So what I want to go into a bit more details is then some general considerations on particle dark matter candidates, knowing that the most, let's say, well-motivated non-particle dark matter candidates are primordial black holes. For which I'll spend 2 words tomorrow on them. Okay, so let's forget particle dark matter candidate. Let's focus on particle dark matter. So, and first, let's see what are the main, like, the constraints that we can set on the particle dark matter mass based on very general arguments. So, what is the range of variation of particle dark matter masses that we can have allowed by observation of evidence of dark matter in astrophysical system? So, let's first consider fermionic dark matter. So dark matter is in the form of fermions, so that respects the Fermi-Pauli distribution. So if we consider a constant sphere of dark matter with mass m and radius r, then the energy that a fermion has can be written as a function of m for me is the dark matter particle mass times the fermion, so the dark matter density, and this is the dark matter particle density, which depends on the total mass, and we are in the simple case of a sphere. So the fermion dark matter energy will be related to the mass of the dark matter and the total mass and the radius of the object. Now, you can also define, so associated to this energy, there is a Fermi, the velocity of the fermionic dark matter, which is related to the energy. Okay. So then the velocity of the fermions in that object I lost the n somewhere. This. And together, if you are in this object of mass m and radius r, there is also an escape velocity associated to that. Okay. So if the velocity of the fermions is larger than the escape velocity from the object, then this sphere of mass m and r is unstable, and the object will simply evaporate because of Fermi degeneracy pressure. So there is this condition that has to be imposed in order to be able to observe astrophysical objects that we see, like, for example, galaxies. So let's take the smallest galaxy that we know, which are dwarf galaxies, and some proxy for the mass and the radius. So let's we measure. We observe dwarf galaxies, and we know that there should be that matter from the kinematic of the stars in the dwarfs that points towards a source of gravitational potential which is not luminous. Let's take a typical dwarf galaxy as a mass of 10 to the 7 solar masses and a radius of 2 to 3 kiloparsec. So by requiring that the velocity of this fermionic dark matter in the object is lower than the escape velocity, then we can set a lower bound on the mass of fermionic dark matter. This goes under the name of Tremaine gun bound, and it tells you that if you want to have a particle dark matter candidate that is a fermion, you cannot have masses of these candidates lower than 100 electron volt. This is not sharp, you can refine it, it was just an example, but in the end it should be larger than 1 to 100 of electron volts. Okay. Continuing this kind of arguments, we can then check what are the conditions for bosonic dark matter. This will be the last thing that I do this morning. So if dark matter instead is made of bosons, then Fermi statistics does not apply. So this bound is left. And question is, what is the minimal mass that dark matter boson should have? Okay. So in this case, we can always use as a reference a dwarf galaxy system. And in this case, however, the condition on the mass will come from the uncertainty principle. So in this case, because of the uncertainty principle, the accuracy at which we can, the precision at which we can determine the velocity of dark matter should be larger than 1 over the radius of the object and the mass of the particle. I'm plugging in some numbers. And divided by the mass. So now the typical escape velocities for this kind of parameters, you can compute further, is of the order of 20 kilometers per second. And this means that the mass has to be larger than 10 to the minus 22 electron volt in order for the uncertainty principle to hold true. So it cannot, we have a lower limit on the mass of the dark matter if it is made of bosons of 10 to the minus 22 electron volt, because quantum pressure induced by the uncertainty principle will not sustain the formation of bound objects that we observe if the mass is lower than this value. And these very ultralight dark matter masses are candidates that are known as fuzzy dark matter, where this lower bound has been pushed to higher masses by setting constraints mostly from cosmological and large-scale structure arguments. Okay? So there is a huge variation in masses. Question is, what is the maximal possible mass? And this is about the Planck mass, about which is not possible to localize the particle any longer. So what we define as particle dark matter roughly is a mass range that goes from 10 to the minus 22 electron volt to more or less the Planck mass. And if we want then to have heavier objects, then we are ending up discussing about non-particle dark matters like primordial black holes. Okay, so tomorrow we'll see other dark matter particle properties and how we can constrain dark matter interactions with astroparticle observables.